Hi, hello, welcome. This is Tej Bhargav from Institute of Aeronautical Research and Engineering, bearing roll number 22951A67F2 from Data Science. Today I am here to explain you about the water treatment. Our goal is safe and clean drinking water. Requirements. Identify the source water in terms of quantity and quality. Second thing, location. Third thing, cost and sustainability. Protect source from contamination like watershed management plans and etc. Appropriate treatment of raw water like source water and safe distribution of treated water. Clean, safe drinking water at the tap. Conventional drinking water treatment. Design or primary objectives are removal of microbial pathogens or coliforms. These were health concerns. Particles like color and turbidity, health and aesthetic concerns. Total dissolved solids removed, hard waters, health and aesthetic concerns. Secondary objectives are removed of dissolved pollutants, health concerns. General, order, taste, pH, inorganic, hardness, alkalinity, FeCl, FCa, Mg, Cu, M and SO4 2 minus NO3 minus Hg, Cd, Se, As, Cn minus Bb, Zn, Cr6, Al, B, radioactive materials, residual free chlorine, TDS, organic, natural organic matter, NOM, pesticides, oils, PAH, anionic detergents, phenols. Conventional drinking water treatment. Groundwater in comparison to surface water. Groundwater tends to have the lower dissolved oxygen compared to surface water, can have very little microbial contamination, especially if GW is from a deeper aquifer. Much higher concentrations of inorganic compounds, anions, chloride, carbonates, sulfates, bromide, nitrates, fluorides, arsenate cations, CaMg, Fe, Mn, Al, Hardness is concentration of Ca and Mg in groundwater. Surface waters, high turbidity and microbial concentrations. Next, dissolved oxygen concentrations vary depending on organic matter concentrations. Water intake or infiltration well. Next, there are some particular measures or steps in the turbid water surface. They are water intake or infiltration well, screening or pre-sedimentation tank, turbidity TSS removal, coagulation and fluctuation, turbidity collide removal, setting tank, flux removal, filtration, turbidity TSS flux removal, disinfection and storage. That involves pathogen removal, hard groundwater, accretion, low DO levels, presence of other gases, precipitation of reduced minerals like Fe, As, Mn due to oxidation, softening, removal of calcium and magnesium, hardness, filtration with or without pre-chlorination, turbidity, TSS, colloidal removal, chlorine to prevent biological growth or on filter media, disinfection and storage. Pathogens are destroyed, provides contact time for disinfection apart from ground storage water. Next, conventional drinking treatment process. Aeration, necessary for GWs that are anozoic. Oxidation of reduced forms of Fe2 to Fe3 and Mn2 to Mn4. For as contaminated water, it can result in substantial removal of As2 types of aerators, cassette, fountain, tray, diffusers. Screening, necessary for most surface waters, especially at intake points, removes large floating and suspended debris, solids and suspensions. Discrete particles. Particles do not change size, shape, and specific gravity over time. Fluctuating materials, size, shape, and specific gravity of particles changes over time as they aggregate or coalesce. Dilute suspensions. If concentration of particles in suspension is insufficient to displace water as the particles settle, concentrated suspensions. If concentration of particles in suspension is sufficient to displace water as the particle settle, there is the table in which we learn the relative size of common materials. Like in separation process, we do have reverse osmosis, nanofiltration, ultrafiltration, microfiltration, particle filtration. In reverse filtration and nanofiltration, aqueous salt, we can filter aqueous salt, metal ion, synthetic dyes, lactose, which is also known as sugars. And in ultrafiltration, we can filter milk proteins, gelatin, endoxin reagent, virus, colloidal silica. In microfiltration, we can also filtrate E. coat pigment, red blood cells, bacteria, oil emulsion, blue indigo dye, cryptopotium, Giardischast, human hair, whole both cells, fat muscles, and activated carbon. Microns. Microns involves the size of 0.001, 0.01, 0.1, 1.0, 10, 100, and 1000. Approximate molecular weight will be resulting around 100, 200, 1000, 20,000, 1 lakh, 5 lakh, 1 mm, and 5 mm. Here we have to know one thing. We have to know one thing, that is 1 micro, that is micrometer, is equals to 4 into 10 to 5 inches, that is 1 into 104 angstrom units. Next, particle size. Particle size found in water treatment were material. Coming to the material, like viruses, they will be around 0.005 to 0.001. Bacteria, it will be around 0.3 to 3. Next, small colloids, they will be around 0.001 to 0.1. Large colloids, 0.1 to 1. Soil, 1 to 100. Sand, 500. Flux, 100 to 2000. Here, the units U of A, comma B, where A, U is equals to micron or micrometer, U is equals to 10 power minus 6 meter or 10 power minus 3 mm. Stable particles that must be chemically and physically conditioned for removal. Discrete particles can be removed by settling. Mu is millimicron, which is 10 power minus 6 mm. Next, solid separation, process of sedimentation and clarification. Sedimentation is also nothing but removal of discrete particles less than 1 micron, greater than 1 micron, that are heavy enough to settle by gravity alone. Sedimentation or settling tanks for flux removal as well. Retention time ranges from 1 to 10 hours. Conventional drinking water treatment process is nothing but coagulation. Coagulation and flocculation, turbidity and suspended solids removal. Design objective is removal of colloidal particles 1 m to 1 micron. Can remove bacteria, soil, sand, and clay particles. Concomitant removal of associated compounds or smaller particles like NOM, heavy metals, pesticides, etc. Stable particles in natural systems. Particles in natural waters, generally in the pH range of 6 to 8, are negatively charged. Like charges repel each other and remain suspended in the solution. Stable particles and no aggregation is possible. A turbid solution is possible here. Next, dilute solution in nature. There is nothing but low ionic strength. Particles with negative surface charges will repel each other. Like if at all we know that negative charges repel each other, whereas negative charges, the same charges will attract each other, repel each other, right? Whereas if at all there is positive and negative, these charges will attract each other. But if at all there are same charges like positive, positive or negative, negative, we know that they repel each other. After addition of coagulants to solutions with high ionic strength, Particles with negative surface charges were depicted in the picture. Next, conventional drinking water treatment process. It's nothing but coagulation. Coagulation mechanism involves charge neutralization, addition of Al or Fe salts on and organic polymers provide high concentration of counter ions that neutralizes negative surfaces charges of particles, reduces electrostatic repulsive interaction forces, and net interaction energy becomes attractive, mainly when there was force, van der Waals force involves in that. Next, net attractive forces lead to aggregation and settling of aggregates or flux information. Sweep flux formation, precipitation of salts at higher concentration. In settling the precipitate, sweeps colloidal particles along with itself. Interparticip- Interparticiple bridging. Polymers attach to more than one particle leading to aggregation and flux formation. Next, residual turbidity results. In residual turbidity results, a rapid mix for 2 minute like speed of 100 RPM. RPM is nothing but revolution per minute. Next, flocculation for 15 minutes, speed 35 rm, settling for 1 hour, then filtration of supernatant through coarse filter paper. Procedure for coagulation and flocculation in the laboratory flocculator. 0 mg by L, 1 mg by L, 2 mg by L, 5 mg by L, 10 mg by L, 20 mg by L. Samples from the coagulated and settled supernatant from the jars after step 3. Next, conventional drinking water process using flocculation. Flocculation or mixing is nothing but rapid mixing for the mixing the coagulant. Detention time is approx 0.5 minutes. Next, slow mixing for flocculation, flux formation. Too fast will break flux. So slow enough to maximum number of particles collision. Optimum speed has to be determined experimentally. Practical examples were milk and tea as colloidal suspensions. Conventional water treatment process. Filtration. Filtration is like a removal of flocculated particles of smaller size that cannot be removed by settling. Rapid sand filters like higher throughput, slow sand filters like lower throughput. Adsorption is another important mechanism for particle removal. Backwashing of filters is essential to regain the head loss due to clogging. Generally, with chlorinated water to disinfect the filters here. Next, disinfection. Destruction of vegetative pathogens, not sterilization, which implies destruction of all life forms like microbes, spores, cyst, virus, etc. Autoclaving, membrane filtration, physical methods, membrane filtration, radiations, UV X-rays, gamma rays, etc. And chemical methods like disinfectants, chlorinated compounds, chlorine, chloramines, chlorine dioxide, ozone like hydroxyl radical mechanism, potassium permanganate involves in the disinfection of destructive vegetative pathogens like not sterilization, which implies destruction of all-time life forms, microbes, spores, cysts, virus, etc. Autoclaving membrane filtration and physical methods like membrane filtration, radiation, UV X-rays, gamma rays, chemical methods like disinfectants, chlorinated compounds, chlorine, chloramines, chlorine dioxide, ozone, like hydroxyl radical mechanism, and potassium permanganate. Next, chlorine remains the most popular. Why? Have you ever gone doubt that why always the chlorine remains the most popular? Let's know into what is the main reason for it. Next, potent germicide like high oxidation potential. Next, a residual and distribution system. Next, chloramine can do the same, but is a less powerful oxidant. Okay, taste and odor control. Oxidation of NOM and removal of compounds causing taste and odor problems. Next, biological growth control. Growth of algae and bacteria in storage reservoirs and water supply systems, like chemical control, like iron and manganese removal, oxidation of SOCs. Problems with chlorine. Hazardous material like difficulty in transportation, handling, storage, and pungent compound, disagreeable taste and odor, thermal and eye irritation, microbial resistance to chlorine, more effective against bacteria rather than spores, cysts, and viral particles. Disinfection by products like DBPS formation and potential health hazard, carcinogenic, mutagenic, tetragenic, and non-carcinogenic. Sorry, excuse me. A little information or discussion in literature. Next, chlorine chemistry. Reactions in water. Addition of chlorine to water results in the formation of hypochlorous HOCl and hydrochloric acids. Cl2 plus H2O gives rise to HOCl plus HCl, whose pK is 3.39. Depending on the pH, hypochlorous acid partly dissociates to hydrogen and hypochlorite ions. HOCl gives rise to H plus OCl minus, whose pK is 7.57. The hypochlorite ion then most often degrades to a mixture of chloride and chlorate ions, 3OCl minus to 2Cl minus plus ClO3 minus. Next, hardness. Hardness due to presence of cations like Ca and Mg. Other cations like Fe, Mn, Sr, Al, etc. may be present formation of soap, curd, like lack of frothing of forming that is essential for bringing dirt particles into solution. Increased soap requirements and subsequent difficulty in all cleaning activities. On heating scale formation or precipitation of these ions, CaCO3 and MgOH2 minus leads to residual efficiency of heating elements and failure. Synthetic detergents can reduce the problem but not eliminate it. General levels of acceptance is less than or equal to 150 mg per liter. Carbonate hardness. Due to anions like carbonates and bicarbonates, also called a temporary hardness, since it can be precipitated by boiling. Non-carbonate hardness. Amount of hardness in excess of carbonate hardness. Next, hardness classification. Description. Soft, moderately hard, hard, very hard. Hardness is less than 1, then less than 50 to 75. Moderately hard, hardness is 1 to 3, then hardness is 50 or 75 or to 150. Hardness is 3 to 6, then hardness per mg per liter is 150 to 300. Hardness is greater than 6, then hardness also will be in greater than 300 for hardness in mg by liter, which we have to know it. Next, alkalinity. Alkalinity is the measure of water ability to absorb hydrogen ions without significant pH change, buffering capacity of water. Softening. Surface water are generally softer than GWs. groundwater. For hardness levels is less than 200 mg by L as CaCO3, no softening is required. Softening is often required for GW, especially when hardness is 1000 mg by liter. Process lime soda gives crude levels of removal or cheap uh, quick lime CaO or hydrated lime is added to water. Carbonates of Ca precipitate of solution. MgOH2 precipitate at pH is greater than 11. Like excess lime has to be added, can bring hardness down to 30 to 40 mg by liter of CaCO3. Ion exchange for finer applications expensive for less than 30 to 40 mg by L of CaCO3. Zeolites can be natural or synthetic. Ion exchange presence cationic or anionic. Na plus or H plus is exchanged for Cf or 2 plus and Mg2 plus. Does not contribute to hardness. Regeneration required much higher removal efficiency can be achieved. Next, water classes based on salinity, like water class and source and TDMS. Fresh from rivers, water and groundwater less than 500. Slightly saline like groundwater, the ground, river and lake 5 to 500 to 1000. Mildly saline estuaries like 1000 to 2000. Moderately saline inland and brackish mix 2000 to 10,000. Severely saline inland and coastal 10,000 to 30,000. Seawater offshore seas and oceans 30,000 to 36,000. TDS is A into star, that is A equals to conversion factor 0.05, 0.55 to 0.75. C electrical conductivity, micros or micros. TBS is equals to total dissolved solids mg by L. Demineralization of TDS control. Process of removing TDS from water membrane process like electrodialysis and electrodialysis reversal like EDR and reverse osmosis like RO, distillation and freezing. Distillation and RO account for 87% of desalination capacity in the world. Next, demineralization. Process of removing TDS from water membrane process, electric current driven electrodialysis or electrodialysis reversal, pressure driven like reverse osmosis, nanofiltration, nanofiltration, ultrafiltration, and microfiltration. Next, distillation. Multiple stage flash distillation, MSF, multiple effect evaporation or distillation, MED, vapor compression or VC, and solar distillation, and at last freezing. Okay, thank you. This is my end of the slide.